I want to believe that both of you were clear when we started the linear programming envelopment analytics. We drew everything using graphs and were able to demonstrate and show clearly how to estimate efficiency. Do you all remember?
Yes, Prof.
Yes. We showed how to estimate efficiency, and it was all fine. It was all good. Now, what we want to do now is we want to see how to estimate efficiency mathematically. Mathematically. Okay. How to estimate efficiency mathematically. How to model the efficiency of a decision-making unit using mathematics. Along the line, we'll try and understand some few things, such as things like, what is lambda? Okay, what is lambda? We shall try and understand what lambda is. But not only that, we'll also try and understand dominance. Dominance. What really is dominance? What is dominance? We'll try and model the understanding behind dominance. And then mixed efficiency, general efficiency, benchmarks, peers, skill efficiency. We'll try and this is where the real linear programming envelopment analytics begin. This is where the real. So let's look at it. First one. So one of the first things you want to take note is that you can assess the efficiency of a DMU using linear programming rather than using graphs. Because linear programming can handle multiple inputs and multiple outputs, complex factors than simple graph. Simple graph, when the inputs are 3, you cannot do 3D easily. When the input, but I can show you a couple of 3D graphs and it's even complex to look at it. But life itself is not simple. Life is complex in real life. Okay? But the simplicity is only used to lay the foundation, after which you then go to the real thing that is not basically about simplicity. So what we are going to do now is we are going to try as much as possible to understand and use mathematics to get the whole complexity. So how do you begin? The first thing you want to do, I'm showing my screen. Do you still see my screen?
Yes, Prof.
Fantastic. But before that, let's refresh our minds when it comes to the concept of convexity or convex combinations. Now, let us assume that we have a point A and point B. Point A is 4 and 6. If you really want to plot it, you can have something like this. In fact, let me use a proper, graphic. So you can have something like this. Okay. And then you can also have something like that. And you'll be able to identify from here clearly that this is X and this is this is Y. That is X, this is Y. So you have X and Y right here. Now, if you want to identify point A, if this is 4 and this is 6, because the 4 is the X variable, the 6 is the Y variable, the 6 is longer than the 4. So let's put it here. The two of them will meet at a point here like this. And so we can say that this point is representing A. Now we want to identify another point B, which is 6. So 6 will be to the right of 4, making it go somewhere here. Okay. And then the 8 might go further. So we put it somewhere like, let's just say here. So this is another point B. Now, so if you look at the content here, there are two data points. You've got an X and Y coordinate. Then let's identify point C. If you check carefully, point C is 5 and 6. 5 is between this 4 here and this 6 there. So 5 is going to be in between. Okay. And then we have 7. 7 is also going to be in between the 6 and the 8 for the Y variable. So that is going to be somewhere there. So if I had to identify what this variable is, I will put something like C somewhere here. Okay, that's C. And so we can draw a line, but what you didn't know is that the line was originally drawn long ago, just as we didn't indicate. We can say that there's a line which is a linear combination of A and B. There's a point between A and B, okay? And that point is point C, and C is a linear combination of A and B. Therefore, C is a convex combination of A and B. Now, we don't need to find the coordinates of C because you can see that we can use some analysis to identify what the coordinates of C are. Okay, how? Well, if you check it even graphically, you will notice that if I take the value of the first one, which is 4, okay, and the second one, which is that, okay, and then I take 0.5% of 4, I'll get 2. And I take 0.5% of 3, I'll also get 3. And I will add the 2 to the 3, and that gives me the 5, which is a coordinate of C. So we can say that C is a convex combination of A and B. C can be obtained provided I take some weight and I multiply that weight by A, and I multiply that weight by B. I should be able to get C. This principle of convexity, which comes from the idea of the straight line, okay, because a straight line is y is equal to mx plus c, and any time you have 2 points, a linear combination of them is possible. This principle can be used to mathematically generate a linear programming algorithm for the envelopment analysis. So we want to be able to generate our analysis. How do we find efficiency? Well, first of all, we can find efficiency provided something is there. One, note that X and Y is a feasible input-output correspondence of the DNA. So when I go into the data set, I can actually see inside the data set like this. I can see that there is a combination, there is something here. And that's something that there is. It is actually X and Y. It has X coordinates, okay, and it has Y coordinates. And this value is actually a linear, it's a point inside the production possibility set. Okay, that's a point inside the production possibility set. The entire set here is a side, PSI, of our table that we identify. If that is the case, then we can identify a constraint of the input. I'm going to wipe out this because this is a detailed analysis that you should understand. You should understand one time. So normally, I think I was supposed to just let it think about it. The graph I just showing without the pauses. So if I take any of the inputs x1, okay, and by the way, in case you've forgotten the data set, this was the data set we are analyzing all this. Okay, if you take x1, if I want to actually identify this technology set, the technology set contains all of this information, okay? Information on input and output. So I will need an input. But this input is a linear combination of these numbers, isn't it? It's a linear combination of the numbers. The same way I told you that, if you can remember, I told you about 4, 6, and then I told you about 6, 8. Okay. So if you check 4, 6, if I multiply the 4 by lambda 1 plus the 6 by that same lambda 1, okay. Oh, sorry. If I multiply the 4 by the lambda 1, yes. And then I do that of the 6 by another lambda 2, and then the 8 by another. What I'm doing is that I am adding these numbers after weighting them. I will be able to get a certain value. I can get this value, x1, if I add these ones together. But in the process of adding these ones together, I must understand that each one is weighted. So the entire technology set, if I want to draw a technology set, okay, whether it's a constant returns or a variable returns technology, the entire technology, if I have this XY graph, if I want to create a production function here, but then I want to make it piecewise using the line, piecewise like this, okay, this line and that line and that line. If I want to create a piecewise line so that this portion here becomes the production set, all I am doing is that I am just taking these values and adding them. But don't forget that in the process of adding them, I am weighting their importance. Therefore, we can say that this x1 is a linear combination, or any of the x's is going to be a linear combination of these. And these ones, I don't know how much weight I can assign to this. So I will just say that let's call the first one lambda 1 because it's the DME1. Let's call the second one lambda 2 because it's DME2. Let's call the third one lambda 3 because it's DME2. That's the weight I'm assigning to each one of them. Okay. Before I add them, I'm assigning weight. The same thing when I go here, if I want to know the value here, if I want to know any particular or what make up the entire x2, the matrix of the x2, I just have to add the lambda 1 to this. And then in the process of doing that, I am summing them. And that is how come you're about to see, because the entire production possibility set is made up of these numbers. We are not touching the y, but we'll still sum them. Mathematically, as for mathematically, the y would also have to come. But graphically, we assume that they are 1, 1, 1, so there's no need to draw. But then mathematically, you have to bring it, even though it may not have any significant impact. So on the basis of that, we can go ahead and say that our x here is equal to, let's deal with equal to first. We'll come and talk about the sign. Our x here is equal to the 2 plus the 1 plus the 2 plus the 3 plus the 5. This will give us an input constraint. Okay, assume that there is no sign for the point. There's no sign there for that. Okay. So x is equal to. Now the question becomes this: what does this mean? The right-hand side. Well, the right-hand side here is dealing with that technology because this is what makes up the technology for that input. And then for the x2, this is what makes up the technology because you are adding all of them for that input. And then the y, this is what makes up the technology for that output because output we are adding them. Okay. This is generally the technology set. So assuming this left-hand side is not there at all, assuming all of these are not there, forget about all these. Then what is left here, this very one here, represents the technology. The question is, and of course, once you have this, then the non-negativity constraint from linear programming should indicate that the weight you are assigning to the DMU should be non-negative or should be 0%. This is a usual one. But So suppose I pick any input inside this entire technology. Suppose this technology is looking like that. Okay, you have X1 and then you have X2. Suppose I come in here and I've not drawn this in, but this whole space here is a technology. Suppose I pick an input X1, okay, or X2. That input will have a coordinate. It may be either inside this technology that I would have drawn. Right now, you don't know the technology. I'm not drawing it yet, but I would have drawn it based on the data set. Suppose that I close my eyes and pick an input or a DMU here. That particular DMU may either be inside the technology I've demarcated, outside the technology I've demarcated, or on the technology frontier that I've demarcated. It may either be inside, outside, or on it. Now, whether it is inside or outside on it is the symbol that is in question here. So if you look at this very one here, okay, let me down. Good. If you look at this very one here, the symbol says that that one I just closed my eyes and collected. That input is more than or equal to the technology. It's more than, the resource is more than or equal to the technology. Now, when it is equal to the technology, what does that mean? It means that, so when you have equality, it means that whatever is on this point, so let's say that this value is 4, it means that the right-hand side value will also be what? If it is not equal to, sorry, if it is equal to, suppose you have this, okay, and you have the X1 here, you have the Y1, X2 there, and then you have demarcated a certain, frontier curve, and you have equal to, and you know the X1 is actually 4, what will be on the right-hand side? What value will be on the right-hand side? Or what value should be on the right-hand side?
I expect it to be 4 as well.
Exactly. We expect it to be 4. And so, because we expect it to be 4, it means that that value, because remember, I did say that this is the technology, the boundary of the technology. Okay. Now, it is a boundary of the technology when there is an equality sign. So if this is also going to be 4, then it means that that value is actually on the frontier. It is on the frontier. Now, if the technology is rather less, because you see, when it is greater than, it means that the technology is less than it, isn't it? When X1 is greater than the technology, it means that the technology is less than X1.
Yes.
Okay. So in that case, it means that that technology, because remember, we are in the input-input graph. So if the technology is less than the X1, it means that that variable is inside the technology. That X1 is inside the technology. For the technology to be what? To be less than it. Or for the variable to be more. Because if you look at this value here, and you connect it to here, okay, the corresponding value on the graph here, if this corresponding value on the graph, if you match it down, it gets to say 2. And then if you correspond it also down here, okay, it will hit the frontier here. And wherever it hits the frontier and you match it leftward, okay, you will also get some value here, say 0.5. So on the frontier, and then yet this value here is say 5. And then when you match it up here, this value is say 5. So it means that wherever this value is, okay, on the X1 level, because this is X1, it is going to be more than the corresponding value on the technology. It's going to be more than the corresponding value on the technology. Therefore, we can now say that this function here prevents the value to be, or makes the particular x value to be, greater than or equal to that of the technology. But we didn't make it that this value is less, because normally you want the input to be reduced. You want the technology to be below the input. And so the graph will eventually look like something like this. If you want the technology, the graph will be something like this. But if you want the technology to be greater than the output, not input, because this one is input. So this one is input. Output to be Y2 and then Y1. Then in this case, the technology will go this way. And in this case, the technology is rather what? Bigger than the output, than the output in question, because you are increasing the output here. It is this principle that we use to generate the linear program. Because remember, these lines were created as constraints. So we can say that this very example that you see here, it shows that a particular input is greater than the technology or equal to the technology. In other words, your input can be more than what is supposed to be, which means you are inefficient. And this other input shows that your input can be more. So that greater than sign is allowing for inefficiencies to happen. And the equal to sign is allowing for efficiency to happen. So these two are very, very important factors that you want to take note of. Now, the next thing is the Y. You see, the output is something that must be bigger. When you are in the technology set, your output must be equal to that of the technology is saying. If the output is equal to, then it means you have produced what the technology is required of you. But if the output is smaller, like you see here, Y is smaller, it means that you haven't produced the output you're required to produce. So you are inefficient. So inefficiency takes the less than part, whereas efficiency takes the equal to part. Now, the non-negativity constraint will still hold. This is a final assumption that we have brought in to exhibit the variable returns to scale assumption. This final assumption says that the weight that we've selected here, the weight, the lambdas that we've selected here, when you sum them up, they should be 100%. In other words, what are the lambdas actually doing? The lambdas are the importance you are assigning to any of your colleague members. The importance you are assigning to any of your colleague members to helping you to gain or to obtain the efficiency that is the highest. Because your efficiency is not determined alone by you. Your efficiency is determined by other colleagues. That's why it's a relative efficiency. And so the weight you are applying to DME1, the weight you are applying to DME2, the weight you are applying to DME3, the weight you are applying to DME4, the weight you are applying to DME5, these weights, these importance, these multipliers are necessary for you yourself to determine your efficiency. Now, if the weights add up to 100%, it means that you are preventing the curve to be proportional, equiproportional to infinity. In other words, you are limiting the importance you can put. So you cannot put more than 100%. You see, 100% is the maximum limit to which somebody can look at something. And that is why the weights add up to 1. So how do you explain the model? So we can sum all of this together. We can sum all the weights. We can say that this weight is for J. Okay. So this is lambda J. This is also 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 lambda J. If you sum them, you get sum of lambda j. And this must add up to 1. But the beautiful thing is that if we happen to know these values, because they are on the line, this will make up what is known as the virtual DMU. So this first equation is saying that the input from all DMU is weighted, is the weighted sum. That's it. It's a weighted sum of the input of each DMU. So the weighted sum of the input of each DMU, okay? And you can see that this one, the first equation said x1 is greater than that. X1 is greater than that means that input x1 from all DMUs, that is the right-hand side, this one. Input from all DMUs is the weighted sum of the input x1 of each DMU. So x1 is actually an input, and it is input from all of them. So all the DMU's input, it happens to be the weighted sum of the inputs of each one of them. And this is it. So when you come here, this is 2 adding to 1. This is 2 adding to 2. 2 adding to 3. 3 adding to 5. You are summing the input, but you are weighting the input to be able to sum them well. The other input will also say the same thing. So the second equation is very, very important, the same way as the first equation is put. Now the third one is for the output. So output to y is the weighted sum of outputs for all the DMs. Okay, this is important, but if you don't understand, I can explain it further. So let's go back to the production possibility. Every case, you remember that efficiency is possible. Inefficiency is possible. And that is why the inequality sign is included here in the actual calculation. You see, and this inequality sign is important because all points inside the PPS can be expressed as a linear combination of any one of the DMUs. If you have any DMU, you can say that you are a linear combination of all the others. When you meet DMU 1, you can tell it that. When you meet DMU 2, you can tell it that. So, what does the inequality and the equality sign, what do they mean? I've already explained. That they mean that it is possible to waste the resources. It is possible to produce what you are not supposed to produce. You know, sometimes a person can go to a company, the person will be working hard, but that work is nothing to the company because it's not adding anything. The person is inefficient. Inefficiency is possible in real life system. And therefore, it is important for the DMU to look efficient, to try and do things that will make it look efficient. The DMU, the inefficiency is possible here means that the DMU can use inputs less than what it's supposed to use. Sorry, the inputs are supposed to be less, but he can use more of the input. He may use input levels in excess of the minimum requirement for the output level, given the output level. Or alternatively, he's supposed to raise the output, but he will not raise the output. He will not raise the output. He will also not cut the output down. He may actually not do anything to the output, and therefore it's as though he's cut it down. So output has to go up, but when you secure lower output levels than what is expected of you, you will lose. And this is what we have said consistently to be the principle of monotonicity, predisposability. So I've said this already. What will it mean if the sign was equal to? If the sign was equal to, it means that the DMU is efficient. What does that mean? It means that that particular unit has got efficiency score equal to what is required by the system. That's a very beautiful thing. Now we are ready. We are ready to estimate the score, efficiency score for DMU4. You can do the same thing for everyone. Now, for DMU4 alone, what do? The first thing you want to do is to find an input-output correspondence. You see, this NOT xi naught is indicating that this particular DMU we are about to evaluate has been identified as unique DMU because it's the one that is undergoing torture. And that this DMU is feasible within the production possibility set. Feasible here means that he is in the frontier, on the frontier of any kind, but he is not outside of the frontier. So it has to be feasible. It has to be feasible. So if you look at this linear program, to be able to estimate the score, you need the minimum extrapolation principle that was postulated by Panasonic in the book. The minimum extrapolation principle, I've said it last time, that this is the principle that tells you that you should have convexity and you should have free disposability. All of these are possible. So I'm first going to formulate the envelopment linear programming model. You will later understand that it's called envelopment, and hence the name is data envelopment analysis. So this is a data set. We are going to formulate this data set using what you have. Sometimes in an exam, not sometimes, many of times in an exam, I will ask you to formulate the data set I'll give you. I'll ask you. So please learn it. Let's do for this one. So what it says here is that we are trying to find the efficiency of DMU4. Okay. You find the efficiency of DMU4. So how do you do that? Well, what you got to do, and this is efficiency is input oriented, input efficiency. So we are going to use a primal model. Remember, every linear programming with a primal model has got a dual. You're going to use a primal linear model. And the DMU4 is input as follows. The inputs are 3 and 2. So you're going to model this thing in such a way that we'll model it for 3 and 2 for this DMU. But remember, it is in consideration with the other ones. Okay. How do you do that? This is the formulation. Obed and Chris, I want you to take a time and write this in your book. And when you're done, you let me know. Because the more you write this thing, there's slight chance that you'll be able to remember it.
We want to minimize the efficiency score for DMU4. That's the theta star 4.
Yes, please feel free and explain it fully to them.
Now come again.
Please feel free and explain it fully to them from the beginning.
I don't really get to myself, but I'm going the way I understand it.
Yeah, you feel free.
Okay. So we want to estimate the efficiency score for DMU4. So that's the theta star 4. Now in the model, the decision variable is to minimize our theta, given our lambdas and the respective thetas. Now it is subject to the input constraints that we have. That's the X1 constraint and then the X2 constraint. Also the inputs and the outputs, so the X1, X2, and the output, which is the Y constraint. From what we saw earlier, given the data across the Y, the X1, and the X2 for each DMU. So each DMU for the first rule, the X1 constraint, we had for DMU1, X value was 2, DMU2 was 1, DMU3 was 2, DMU4 was 3, DMU5 was also 3, per their respective lambdas. And we suggested that if it is less than or equal to lambda or x1, sorry, less than or equal to x1, then we are creating inefficiencies. It means that the technology is within the inputs. That's what I got. So for DMU4, its x1 value was 3, as we can see, 3 lambda 4. So the right-hand side too is 3. I think we attach a theta. Perhaps suggest that it's an input orientation, I believe. Then we do same for the second input, x2. We take for each of the DMUs their values, x1, x2, x3, x4, x5, 5, 2, 2, 2, 1, times their weights, the lambdas. Then less than or equal to the DMU4's x2 value again, which is 2. When it comes to the output constraint, I think the values we had was 1 across the board. So 1 lambda all true. Then we put greater than or equal to 1. And the understanding we got there was that there will be likely some inefficiencies in the output constraints, unless it is equal to. Then to do the VRS assumption, we are equating all the weights. So 1 lambda 1 plus 2 plus lambda 3 lambda 5 equal to 1. Then we put the non-negative constraint. Yeah. So that's how I understood it.
Right. So Obed and Chris, are you there?
Yes, Prof.
And I just want you to know is that you will formulate I'll give you a data set like this, and you will formulate an input-oriented and output-oriented efficiency score for a particular DMU. So we are formulating the input-oriented, that's why we use theta. If we were formulating the output-oriented, we would have used 5. We would have used 5, 4. Okay. The star here means that we have an efficiency score value. So this efficiency score value can be, say, 0.8. So that means we have the score. But right now, as it stands, we don't have the score. So I am happy to let you know that to get this value, the actual value, say 0.8, we need to minimize theta, subject to the condition that we are going to find the lambdas and the theta. But what do you mean by minimizing theta? The only way to kind of appreciate this, first, you would draw this, let's call this x1 and then this x2. We have the whole frontier generated like that. And what this means is that you have a value somewhere here. Let's call it A. No, that's DMU4. So let's call it 4. And this, then put that on top. So you have DMU4. And this DMU4 has got some coordinates. The coordinates are what you see here. Okay? The inputs are 3 and 2. Okay? And these inputs, which are 3 and 2, are very, very too much. And we want to reduce it. So we are going to go along the radial line. Okay, so this is like the radial line. We are going to go through this radial line, reduce this input in the direction of the origin, like that. So we are cutting down this, but in the process, we'll not get to the origin. The moment we hit that section, which section? This very section of the frontier, we stop. The moment we get to the frontier, we are done. We stop there. We stop here. So the question becomes, what is going to help us? What is exactly going to help us, to be able to do that? God, what do you think is going to help us to be able to cut down the input x1, which is 3, and the input x2, which is 2, down to the frontier?
I didn't hear that.
What is going to help us to be able to cut the input from 3 and 2 to their current frontier level, the frontier level? What is going to help us to do that? What is going to help us to draw down, to reduce those inputs?
By going towards the origin.
Yes, we know we are going towards the origin, but what is going to help us to move towards the origin? And it is something we don't know. It is what? Something that we don't know. And what is that? What is that something we don't know? It is the theta. So what is going to happen is that there's something here called theta. We don't know the theta. This is it, theta. I'm going to multiply this theta by 3. I'm going to multiply this theta by 2. This theta, which is efficiency score, should help me move these actuals to the target. Do you get it now?
Yeah.
It should help me move from the actual to the target. So the actual is what you are having now, but what you are having is too much. So we need to be able to move you to the target. And to get to the target, we need an efficiency score that can what? But the efficiency score, we don't know. And so we formulate a linear programming. And in this linear programming, we minimize theta. Now, why are we minimizing theta? Well, the thing is that as it stands now, if theta is minimized, then you can bring the input down, isn't it? If theta is, for example, if theta was 1, this 1 wouldn't be where it is. The input wouldn't be, because theta is 1 at this point here.
Yeah.
Okay.
Yeah.
So theta is going to help us to minimize these inputs. And that is why you can see that on the right-hand side, we have each of the inputs being multiplied by theta.
Theta.
So we multiply each of the input by theta, and it will reduce, because right now theta is not 1. Because if theta is 1, the input will be here. So theta is a certain number. We don't know. Okay. So that certain number, let's say it's 0.4. That number is going to be multiplied by this value. It will bring the value down to this section where it's supposed to be. But how do we get theta in the first place? We can get theta through this optimization process by first minimizing theta, subject to the constraint that we should find the lambda. Once we get these lambdas, the weights assigned to each DMU. And remember, I am just doing for DMU4 now. I'm just doing for DMU4 now. So for this DMU4, I will formulate this model. When I am done, I will do for DMU1. I'll formulate another model for DMU1. When I am done, I will do for DMU2. I will do for DMU3. I will do for DMU5. And now for each one at a time, I will formulate the model. Don't worry, the software will do it all automatically in seconds for you. Now you just have to know the principle. And for each one of them, when I'm formulating the model, my goal is to get this one. That's why they are bottom, they are below. My goal is to get this weight, and then get this decision variables. Once you get this decision variables, this of course also becomes the objective function. The theta is objective function and it's also a decision variable. Okay. Once you get this decision variables, the lambdas, you substitute the lambdas on the left-hand side, and you can now easily get what theta. So let's say that you substitute the values on the left-hand side. You get the left-hand side to be, say, to be 6. Okay, you get this one here to be 6. Then it means that you can find theta, because theta, you divide both sides by 3, you divide both sides by 3, and once you divide both sides by 3, divide this by 3, you divide this. Suppose it was 6, divide 6 by 3. It's going to be, okay, this is an input oriented, so obviously the value should not be that. So let's assume that it's rather 2 instead of 6. So you divide 3 by 3, you divide 2 by 3, and you're going to get 75%, which means that the actual efficiency score for this firm is what? Is 75%. Theta value is 75%. So the essence of the whole process is that, so what is on the left-hand side? The left-hand side here, everything on this left-hand side here, remember, is a technology. This will not change when you are formulating the model. I want to repeat. the technology will not change when you are formulating the model. In other words, the left-hand side of this optimization, this is a primal model. The left-hand side of this primal model will not change because it's going to be the same for everybody because everybody is facing the same technology. What is going to change? What is going to change is the right-hand side. So each time I'm formulating that of DMU4, I'm going to use this value of 3 and 2. Good. But what if I'm formulating for, so DMU4, you can see that I'm having 3 and 2 here. Okay. But when I'm formulating for DMU1, I have to deal with what? 2 and 5. And when I'm formulating for DMU3, I will have 2 and 2. It is critical that you understand the formulation process. Now, another thing is that if it is an input orientation, this is a minimization of theta. And the theta is multiplied by the inputs, but you don't multiply the output because it's not output orientation. So you can see that output is here, but it was not multiplied, the right-hand side value. These are the input and output on the right-hand side. They are the input and output of the DMU under evaluation, which is DMU4. Its output is not multiplying the theta because we are doing input orientation. So the input is multiplied by theta. But suppose we were doing the output orientation. Let me tell you what would have changed. This minimize will go to maximize. This theta will go to phi, will become phi with a star. And this theta will become phi. And this one will also become phi. And on the right-hand side, you will not multiply this 3 and 2 by that. The 3 and 2 will still be there, but you multiply the 1 rather by 5. So in an output orientation, the phi is given to the output. And in an input orientation, the theta is given to the input. Everything else on the left-hand side remains the same. Nothing changes. The only thing that will change is when you change the DMU. In this case, you use those variables on the right-hand side. Yes, go ahead.
How about the signs? The signs remain the same.
The signs will all remain the same. I'll come and talk about this. The signs will not change. Nothing of the signs will change.
Okay.
Now, if you want to add a convexity constraint, this will also be there for the VRS. It will not change. It will be that. But if you are doing constant returns to scale, then you will remove this VRS constraint. It will not be there. So this VRS constraint is the one where the curve bends, convexity. But CRS is when the line is just straight, constant returns. So when it is constant returns, you don't bring this constraint number 4. And you don't also bring the theta free. But when it is variable returns to scale, you bring this constraint and you bring theta free. So if I were to tell you to formulate that of DMU 5, would you all be able to do that?
Yeah.
Obed, would you have been able to do? Chris, would you have been able to formulate if it was the DMU 5 instead of the 4 we are doing?
Yes.
What would have changed here? Look at the DMU 5. That is a DMU 5
So
here. So now when we go here, what would have changed?
The 2 become 1.
And then?
Can you go back?
What else would have changed? 6 things would have changed. You should be clear. What would have changed? Obed.
The width.
It seems I'm confused here.
But you should have asked me before I asked you, right? Yes, Chris, I'm still waiting for you. What are you confused about?
Unless the two things are side by side. Okay, let me see.
So, Godwell, coming back to linear programming, this on the right-hand side here is we call it the outcomes. If it is output, is the outcomes. So this constraint here is the output constraint outcomes.
Okay.
Then these are resource constraints.
Yes.
These are input resource constraints. And when you look at the right-hand side, you see, the way we call linear programming is very important. Normally, if it is resources, the right-hand side are known as the available resources.
Yes.
Available resources. That's what is
Yes.
on the right-hand side.
Yes.
And then the left-hand side is the used resources.
Reused. Yes.
The used resources. And when the available resources are being fully used, then it means that the equality is there.
Yes.
Now, in this context here, one of them is the input that is used and input that should have been used.
Okay.
Input that is used and input that should have been used. So the right-hand side, the left-hand side is still the same thing. Is the resources that are used. And then the right-hand side is resources that should be used.
Okay.
So, but in reality, when you go to the data, it's actually your actual input.
Mm-hmm.
The right-hand side is actually your actual input.
Okay.
But then it's also being multiplied by theta.
Theta.
So it's not fully your actual input. It's like here it is your actual input, but it's the input that should be used. But then out of the input that should be used, okay, sorry, here, the left-hand side is the input that should be used. And this right-hand side is the input that is used.
Oh,
So
for the DA, for the DA.
For the yes, DA approach. In other words, understand that when you look at this, the left-hand side here is what is inside the technology. Is a technology, is a frontier. Is a frontier part. Or let's put it this way, is a technology.
Yes.
Not just a frontier, because it becomes a frontier when it is equal. When it is equal. But is a frontier together with the space on the frontier.
Okay.
So is that whole set of polyhedron. So if you are efficient, what it means is that the input you have used, this input is exactly the same as what is inside the technology, what is on the frontier. And if it is what is on the frontier, then you have an equality.
Right.
But if what you have used, okay, is more than what is on the frontier, if what you have used is here.
Yes.
Okay. If what you have used is more than what is on the front, or what is in or on the frontier, because we don't know yet. If what you have used is more, it means that the frontier will be less, isn't it?
That's it.
It means the technology will be less. So it means that you are inside the technology. You are inside the technology. The technology, this whole thing is not just one thing. It is, like I said, it is a whole thing. If you look at it, okay? If you have something like this, it is aligned together with the space, the whole thing. So if you are using too many inputs here, then it means that you are dealing with the less than part of this thing, because this thing, okay, you are inside the thing. Let me put it up. Let me put it. So you are more or less using too many inputs than what the frontier is telling you. So the frontier is less than you, and therefore you are more than the frontier. If you are here, you are more than the frontier because the frontier is below you. So you are not part of it. But if you are here on the frontier, then it means that you are dealing with the equality part.
Yeah.
So you are on the frontier. And it's not just the frontier, but it is. So because this one is fixed, everything on the left-hand side is fixed. And it is the whole of this space. You are either on the far right of it or on the far left of it.
Yeah.
So you've got to connect this one to the resources that are being used and the resources that are actually used. And you have to connect it to the, what we call the slacks. Because you see, the input slacks are going to be there when you have some input you are supposed to use. For example, let's say that you are using an input here, which is 3. And then you are expected, you are way above what the frontier is saying. The frontier says it's 2, but you are using 3. It means that you are inefficient, first of all, isn't it?
That's it.
On that particular input, you are inefficient. And if you are inefficient, it means that you are above the frontier. And so you are creating some resources. There are some resources that are left over.
Yeah, slacks.
Slacks. The only thing is that the basic model here doesn't really show us the slacks. And that will be for another day. So you want to be able to understand this as it relates to linear programming a lot. The decision variable. The first thing about linear programming, you should know your decision variable. In linear programming, the decision variables normally are the x's. Now here, the decision variables are the lambdas and then the thetas. Take note. This is the decision variable. Number 2, you must know your objective function. In usual linear programming, your objective function is z, which is equal to some things, coefficient, multiplying some, variables, isn't it?
Yeah.
Okay. You have some coefficient C1 and C2 multiplying some variables. Now here, that z value is still the theta here. So your objective function value is the theta. It is an efficiency score here.
Right.
This is very important. Then the next thing after the decision variables and that of the objective function. Ooh, please, just a second. I mean, you understand that this refers to the non-negativity constraints, right?
Yes, please.
Okay, because of this sign. So this means that the weight you are assigning to each company, each DMU, when you are determining your efficiency, your theta, that weight you are assigning, the weight should, first of all, you already indicated that the weight should add up to 100% here. And what you are saying is that the weight should also be 0 or positive. In other words, you don't want any weight that is negative. There's no assignment of a weight that will bring you down. At least it should do you nothing, which is 0, or it should bring you up, which is positive. The importance you are assigning to each DMU. And the DMUs are made up of input and output. Don't forget, the DMU is an input-output correspondence. So when you take 2, 5, it's a DMU. It's an input-output correspondence. When you take 1, 2, it's a DMU. It's an input-output correspondence. When you take 2, 2, 1, it's a DMU. It's an input-output correspondence. When you take 3, 1, 1, it's a DMU 5. So you have lambda 5, lambda 5, lambda 5 in that vertical fashion because it is an input-output correspondence. So any of these DMUs, you are taking them into consideration when you are trying to estimate your efficiency. That is DMU force efficiency. So the constraints here are dealing with, so first we said objective function. Sorry, the decision variables are the lambdas or the weight. Then the objective function, the decision, the decision variables are both the lambdas and the thetas. They are both the lambda and the theta because they are inside the constraint. Check them. Okay, they are inside the constraint. All letters that are inside the constraint are decision variables. All letters like theta, like lambda, Greek letters, they are all decision variables. Okay. All right. So let's move on. So this is the, come on. This is the way you want to understand. If there's any question you want to ask, decision variables are the lambdas and then the theta. Then the same theta becomes the objective function value. Then the constraints are this. You have the left-hand side constraint, okay? Left-hand side constraint, and then the right-hand side constraint. And then you have the convexity constraint, which is a VRS. And then finally, the non-negativity constraint. That is it. Any question? So you should know that the technology is the left-hand side, and then the right-hand side is the DMU under evaluation. It's input and output. And when you are doing input orientation, you give the theta to the 3. When you're doing output orientation, you give the theta to the 1. Or when you're doing the input orientation, give the theta to the inputs. All the inputs, if there are 17 inputs, all of them will have theta, 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 theta. And you have to formulate this when you are writing your own thesis or paper. You have to formulate this in your thesis. And then you do that. Anytime there is a hypothetical example, you can formulate this. So our goal is that, you see, if it was just single input and single output, it was just x1 and x2, or lambda 1 and lambda 2, we can use simultaneous equation. But then these ones on the right-hand side will still have theta there. So it's not simple to find an answer manually, even in the 2-variable case, like you would have done in a normal linear program, because the variables that you are finding here are not just 2-variable case. There will always be more than 2 variable cases, unless you have only one DMU, in which case too, there is no comparison. Okay. If you have one DMU, it means that you have 2 lambda 1 and 5 lambda 1. And then nothing else will be here. And then you have 3 theta and then 2 theta. So you can move these ones to the left-hand side equal to 0 and find that. Again, you're not going to get anything. So it's a linear programming. You have to use lingo. You have to use Lindo. You have to use MATLAB. You have to use R or Python or any of the linear programming packages to be able to run it. And that is it. Okay, so let's summarize interpretation. Let's summarize interpretation. The linear programming you see above there, and this is my goal of today actually, is efficiency method. The efficiency is this. And this efficiency score, which is theta 4 star, it is seeking the efficiency score by minimizing the inputs. I told you graphically. You are minimizing the input. Now, how do I know that? You come to the right-hand side here, and you see that, yes, the inputs are being minimized. That is why the input have been multiplied by the theta. Okay. So you are minimizing the input using a factor. So this factor is an improvement factor. Okay. The factor is an improvement factor. And this improvement factor is theta. It is a decision variable. And that is not the only decision variable. There's also a decision variable, which is the lambda in the model. But then the theta will also form the objective function, as you have seen. So what you are doing is you are minimizing this input using this improvement factor theta, subject to the linear programming constraint that the weighted sum of output, the weighted sum of inputs x1 and x2 of all DMUs. Watch that word. Of all DMUs. What does that mean? The weighted sum of input and output of all DMUs. All DMUs here being that you are looking at one DMU at a time, which is DMU 4, but it is subject to the constraint that the weighted sum of all DMUs, that is those on the left-hand side of the equation here, is less than or equal to the input x1, that's the first constraint, and the input x2, that's the second constraint, of the DMU being evaluated. That is the DMU that is being evaluated, the one with the score, with the actual output of input of 3 and 2. That's the first constraint and the second constraint in this case. And that's the weighted sum of the output, because you have to talk about the output of all DMUs too. That's the left-hand side. Should be greater or equal to the output of the DMU and that evaluation. So this is explanation of that information there. Of course, you have the non-negativity constraint and you have the convexity VRS constraint. So there are a few things you want to note about theta here. This is an input orientation. You can do output orientation. And I told you about output orientation as well. What can you do about output orientation? Well, the efficiency score is added to the current input levels of the DMU4. And you saw that here. You add it to the current input level of the DMU.
Is it multiplied by or is added to it?
It's multiplied. The key thing is that once you are not asking questions, it simply probably means that you understand it. So
yeah, but this is sort of in a matrix form, right? So
yes, it's a matrix form. So you can create a matrix for the input and then create a matrix for the output. When we come to the R and we are doing it, you see it beautifully. You see that we'll create a matrix from the vectors and then we'll just use it. Yeah.
Okay.
Very good. So because this is an input orientation, the outputs are kept constant. And you can see that the outputs were not multiplied. And we also kept it 1, 1, 1, 1, 1, 1, which means they have been kept constant. Okay. All right. Next question. I like that question, by the way.
The weights don't sum up to 1 anymore.
Please say that again.
Is it for
Please repeat your question.
We drop it when it is a CRS. So in that case, does it mean that the weights don't add up to 100? Don't add up to 100% or 1 anymore?
God, did you understand this question?
I think it's asking the CRS, why we drop it.
Yeah. The VRS is, you see, whatever combination we have, it should sum up to 1. That's what the VRS is saying. But in the context of the CRS, does it mean that it doesn't need to sum up to 1 anymore?
God, did you understand the question?
But I believe you should explain a CRS drop the CRS there, that's a drop it, if you could just explain it.
Oh, it's a simple statement that says that if you are assuming that you are not dealing with VRS, but you are dealing with CRS, if you are assuming that this industry exhibits constant returns to scale, then you don't need this assumption. You don't need this constraint. This constraint is 0. So you don't even write it. That's the meaning of drop it. So the CRS drops this constraint. CRS kills this constraint.
Okay.
CRS does not need this constraint. That is what that blue statement is saying. Okay, do you understand?
Yes, Doc.
Okay. The next thing. So the next thing to note is that you can formulate the similar linear programming for any other DMU. I've said it already. The left-hand side for each equation will not change for every formulation. I said that before. All you got to do is to do a small change on the right-hand side. But the key point is that you will have to formulate and solve these 5 models because there are 5 firms, 1 for each DMU. But in real life, you are not doing that because the software is doing that. Even if it's 1 million firms, it's doing all of them one at a time, one at a time, one at a time, but it does it quickly at the same time for you. Okay. Now, what is the lambda about? Let's get a little bit deeper into this lambda. What is a lambda about? We've said before that the lambdas are the coefficients. They are the multipliers. They are the importance you are assigning to a DMU. So at the time I was formulating for DMU4, I have a lambda I am assigning. I have a lambda that I am assigned, okay, to DMUs, okay, DMUs that are needed for me to be efficient in the optimization process, okay, DMUs that are needed. So if you are doing it for DMU4, what you are doing also is that you are what do you call it? When you're doing it for DMU4, you have to have it for DMU1, DMU2, DMU3. Actually, you have to consider every one of them. But at the end of the day, the optimization process is going to tell you that, oh, I don't need DMU1 when I want to be efficient. I don't need DMU2 when I want to. So the lambda can say that I don't need DMU1. Therefore, you see that the lambda for DMU1 will be 0. The lambda can say I don't need DMU3. That means the lambda for DMU3 is going to be 0. Okay, like that. So that is exactly what you want to take note of. The lambdas are the important. So if you don't find a particular DMU important, you don't consider that DMU as anything important. The next thing is that the lambda is the weight. But note that the lambda is the weight of the peers. Now, if you don't find that particular DMU as your peer, you will not give it a positive lambda. Let me repeat that. The lambda is a peer. So if you don't find that DMU as a lambda, the lambda is not a peer. Please, does that make sense?
Yes, but in the example we just saw, we had lambda for all the DMUs, even though they are not.
Which one?
The example we just saw.
Uh-huh.
So we did an example for DMU4.
Correct.
And we had lambda for all the DMUs from 1, 2, 3, and 5.
Uh-huh.
But last week we saw that not all the DMUs were the peers of DMU4. So why do we have the lambda for all the? Or it's just the notation?
Exactly. It's just a lambda name. We are just giving the name, but actual value we don't know. So if that particular DMU is useless, at the end of the day, the lambda value for it to be 0 anyway.
So it's for notation purposes.
It's just for notation purposes, exactly. Yeah. Okay. That is why this sentence is saying that the DMUs with non-zero lambda values, those that do not have lambda values that are 0, so they have positive lambda values, they are the ones that are the what? The peers. They are the ones that are the role models. They are the ones that are the efficient reference for the target DMU. That is the DMU you are considering at the time. So the DMU4, if we do it and we check the lambdas and we saw that, check here, we go and check the lambdas, we saw that lambda 1 is 0, lambda 2 is 60%, lambda 3 is 0, lambda 4 is 30%, lambda 5 is 20%. Then in this case, those that have got positive lambda values, they are the ones that are the peers for this one. So sometimes the firm can use itself, to do the thing. The firm can use itself to do, as its own peer. We said that. And in that case, everybody will have a lambda of 0. Okay. The entire left-hand side is the production possibility set. I've said it. The entire right-hand side belongs to the PPS. It is either on the thing or off the thing. Okay. Next one. Godwin, I hope you are following.
I'm following, Doc.
Okay. Now, what does the theta do? I've explained it already, but let me ask you again. What does the theta do? You can tell me. What do you think the theta is doing here?
It helps us reduce the combination of inputs so that we can get to the front.
Say that again.
So it helps us to be able to reduce the inputs or minimize it in a minimization case to be able to get to the frontier while referencing the origin.
Good. So what exactly is it doing to help here?
It is making the DMU at that particular time efficient.
Say that again.
It is making the DMUs efficient.
Exactly. By doing what?
By reducing the inefficiencies. That is because it multiplies the variable. If it's able to let it come, like what Chris said, let it be on the efficient on the line of I don't know how to put it. Let's assume you are on the right hand side of the frontier. Yes, it lets you come and be on the line of the frontier, because you got to know that when you are inside the frontier, it means that you are not being efficient. But you're only efficient when you are on the frontier.
Okay. God, did you understand? You understand?
So like, I think you was trying to allude that if you multiply the theta by the inputs on the right hand side in an input orientation, then it reduces your slacks to makes you efficient on the frontier.
So what the theta is doing is exactly this, and that's I think what most of you will say. A value of less than 1 means the firm is inefficient. In this case, let's say it is 71.4%. It will mean that 71.714 times the current input of the DMU is feasible within the production set. It means that the firm is inefficient by a certain value, and therefore, in order to be efficient, it would have to cut down its input by 1 minus 0.714 times. I'm sure you get it. The last time we explained it. You remember?
Yes, Prof.
Good. So that is how you do it. Now, once you have gotten the value, it becomes optimal. That's why we said the optimal value of theta of the objective function, which is not theta, becomes the input efficiency score for this. So this whole thing, this graphical thing, are what we are just saying. So in general, we can write a complete efficiency model generally without specific one like DMU4. We can now write a general technical input efficiency of a company like this. This can be done using the following linear programming. So first, you write theta, minimize theta, subject to the constraint that we are going to find the weighted sum of input. You can see that the input are being multiplied by theta. This is output constraint. Okay, you see that the weighted sum of output greater than the output of the DMU at the evaluation. The zero not and the zero not means that we are dealing with the DMU under consideration. Okay. Unlike this one where this side is J. The J means that all the DMUs, each one of them at the go, all the DMUs. You have the VRS constraint, which is a convexity constraint, and then you have the non-negativity constraint as well. If you don't understand this, let me know. So this is a general, this is what sometimes you see in journal papers, but you know where it's coming from. We took a specific example and we demonstrated what it is. This is a minimization linear programming primer model, also called envelopment model, okay, in the DA parlance.
Would using the dual reveal the same results, or is just a prime that we could use to?
R will give you the same result when we go and run it. We will run all of this in R and we'll juxtapose it to what this one will do.
I'm asking if the dual form, you say it's primal, so if the dual form will also
yes, there's a dual form of this, Okay, the dual form here is called the multiplier model. We'll look at that as well. The dual forms are usually a bit complex. So that is why I want to do the primal or the envelopment first. Then later on, I'll show you the dual. But yes, there's a dual form of this primal model. You know, every linear programming that is a primal has a dual. Okay, when the dual is unbounded, the primal is infeasible. When the dual is infeasible, the primal is unbounded. It also goes just with the complementary slackness theorem as well. Look at that. So all of these have been interpreted. Okay, whenever you write these models, just know what it is. We know it. We know that this is the efficiency. This is the input of the firm, the particular firm under consideration. This is the output. This is the theta, the efficiency score. It is 1 when the firm is efficient. It is less than 1 when the firm is inefficient. Efficient firms are called frontier firms. Inefficient firms are called dominated firms. Next time, we will continue to look at the further interpretation of this technique. That brings us to the end of the entire Kabudo.